Hello, I am Dr. Imran Khan, and today we will discuss advanced 3D transistors for future generation integrated circuits. So, in this our lecture, we are going to discuss 3D transistor structures in detail, how we can use these transistor structures for our future generation integrated circuits. As all of you know that over the past several decades, the size reduction of CMOS circuits has fueled the growth of the microelectronic industry. The manufacturing cost of integrated circuits has decreased exponentially, making countless new applications available to the general public. In the past, CMOS technology advances relied on improving manufacturing capabilities. So, our focus on today's lecture is on advanced 3D transistors. Okay, so let's start our lecture. So the outline of our lecture is, first of all, we will discuss Moore's law and transistor count, and after that we will discuss changing transistor architectures. We will discuss how we can use these changing transistor structures in our future integrated circuits. Moore's law. In 1965, Gordon Moore noted that the number of transistors on a chip doubled every 18 to 24 months. So he made a prediction that semiconductor technology will double its effectiveness every 18 months. Gordon Moore was founder of Intel, and his law basically drive the semiconductor industry for last 50 or 60 years. So far, this law was successful, but maybe in the future, semiconductor industry may not follow this law. So we are going to discuss in details how it will happen. Transistor count. So as we see from this graph that the number of transistors are increasing in our integrated circuits. So here on the y-axis, it's the number of transistors, and along the x-axis, it's the number of years. So here you can see the microprocessors, different microprocessors introduced by the Intel. So like in around 1980s and to year 2000, and then in year 2020. So here you can see that the number of transistors are continually increasing. So here you can see the relationship, and in the year 2020 we have around 15 billion transistors in our integrated circuits. So as you can see that the number of transistors are increasing. So it means that we are scaling down our transistors. So the architecture of our transistors are continually changing. It means that we are continually decreasing the size of our transistor to integrate more and more number of transistors in our integrated circuits, because we want more functionality in our integrated circuits. Okay, so changing transistor structures. So in this our lecture, we are going to discuss in details about the scaling and the changing transistor structures. So here you can see that a lot of transistor structures here, from planar transistor to the multi-gate transistor to FinFETs and the cylindrical transistor. So we are going to discuss in details how these transistor structures will be integrated in our digital integrated circuits. So basically we are interested to explore about our future integrated circuits. Okay, so let's start scaling to the end of roadmap. So here you can see 32 nanometer, 22 nanometer, and beyond 10 nanometer. So these are the process technologies. On 32 nanometers, you can use planar transistor. Planar transistor means single gate transistor for the fabrication of your integrated circuits. But as the process decreases, around 22 nanometers, these planar transistors are not successful. So there was a need to develop a new transistor structure. So the best candidate for this 22 nanometer was uh, FinFET or the multi-gate transistor structure. So based on this technology, the integrated circuits or chips are already available in the market. But beyond 10 nanometer, we need a new kind of transistor structure, especially around 5 nanometer or maybe lower. So here the best candidate is your stacked gate all around FET. So here you can see this 3D nanowire FET and okay, so BSIM family of compact transistor model developed by UC Berkeley. So BSIM basically stands for Berkeley Short Channel Insulated Gate Field Effect Transistor Model. So it was developed by University of California, Berkeley in 1990s, and this model is now industry standard for the integrated circuits. So here you can see the family of transistor models developed by UC Berkeley from year 1990 to year 2012. So here they have this planar MOSFET models, this SOI models, and this multi-gate transistor model. So here they developed BSIM 1 and 2 around year 1990 and this BSIM 3 around year 1995. So here this is BSIM 4, 5, 6 and after 2005 they developed this BSIM-CMG and BSIM-IMG. CMG means this common gate model for this FET. This is a common multi-gate model. Okay, so these models are used extensively in research organizations and the industry. So before starting our main focus, so we will discuss MOS transistor structure. So as you know that this is our planar transistor model, so the single gate model. So here you can see the source, gate and the drain. So and the p-type body. So this is the simple model for our planar transistor or the single gate transistor model. So you apply voltage at the gate and control the current between the source and the drain. Okay, so how your transistor works. So before going to the main part of our lecture, we will basically discuss how your single gate transistor works. So the MOSFET is basically a metal oxide semiconductor field effect transistor, and here you can see that you can use this MOSFET as a switch. Okay, so how you can use it like a switch. So this is your gate, source and the drain. So when you apply the voltage on the gate and the drain, you control the current between the source and the drain. And so your MOSFET works in cutoff region, linear or triode region and the saturation region. So in your cutoff region and saturation region, you can use your MOSFET as a switch. Okay, so why do we need double gate transistor model? So this was the big question because around 32 nanometer process technology, we were using this bulk CMOS or the planar transistors, and around 10 nanometer, we will use this non-silicon nano devices for the fabrication of our integrated circuit. So there is a gap between 32 nanometer and the 10 nanometer. So this gap will be filled by these double gate transistor model. So double gate transistor models or the double gate FETs, field effect transistors, are basically the extension of CMOS. So its manufacturing is similar to the CMOS models. So what are the key limitations of CMOS scaling? Better control of channel from transistor gates, reduced short channel effects, better on-off currents, improved sub-threshold slopes. So this double-gate transistor models. So why do we need the new transistor structure? Basically, the main advantage of multi-gate devices is improved short channel effect. Since channel is controlled electrostatically by the gate from the multiple side, the channel is better controlled by the gate than in the conventional transistor structures. Unwanted leakage components are reduced and small transistors can be used to continue the cost reduction through miniaturization. So here you can see that uh, uh, the new transistor structure. So the leakage, here you can see that the off current must be suppressed as gate length is scaled on. Leakage occur in the region away from the channel surface. So let's get rid of this. So for this we need the multi-gate transistor. So why do we need this multi-gate MOSFET and the FinFET? The way of eliminating deep leakage path is to provide gate control from more than one side of the channel. The silicon film is very thin, so no leakage path is far from one of the gate. Because there are more than one gate, the structure may be called multi-gate MOSFET. So here you can see that now we have this multi-gate structure. So here you can see the two gates, and here you can see the source and the drain, and this is the channel, and here you can see this oxide thickness. This is the gate voltage, and here now your gate is controlling this channel from both the sides. So it will obviously reduce this leakage currents. So now we will discuss ultra thin body silicon on insulator and the multi-gate MOSFETs. So as you know that reducing oxide thickness gives the gate excellent control of silicon surface potential, but the drain could still have more control than the gate along subsurface leakage current paths. So here in the figures you can see in detail. So here you can see that uh, the ultra thin body silicon on insulator models. Okay, so ultra thin body MOSFETs and the silicon on insulator. Ultra thin body MOSFET built on ultra thin silicon films on insulator. Since the silicon film is very thin, perhaps less than 10 nanometer, no leakage path is very far from the gate. The sub-threshold leakage is reduced as the silicon film is made thinner. So here you can see your gate, source, and the drain, and here you can see this silicon oxide. So the silicon thickness is only 3 nanometer here, and here this is your ultra thin body MOSFET. Okay, so here we have our multi-gate field effect transistors. So now we will discuss in detail our various structures of multi-gate MOSFETs. So in the figures, you can see several examples of different flavors of multi-gate MOSFETs. The FinFET consists of thin silicon body and the gate wrapping around its top and two sides. So here in the figure 1 you can see triple gate FinFET on bulk silicon. So here you can see this is your triple gate, this is your source drain, and this is the fin, and here you can see the gate. So this is your triple gate FinFET on bulk SI, and this is your in the figure B you can see triple gate FinFET on SOI, silicon on insulator. SOI is silicon on insulator. So here is your triple gate FinFET, and here you can see in the figure C it's a double gate FinFET on insulator, and the figure D it's all around gate. Figure E it's independent double gate FinFET on silicon on insulator, and the figure F it's planar double gate SOI structure. So here you can see the different multi-gate transistor structures. So these transistor structures are helpful in designing new integrated circuits. So we can use these different type of structures for our different future digital ICs. Okay, so various multi-gate transistor architectures supported in BSIM-CMG. This CMG is common multi-gate transistor model. It was obviously developed by the BSIM group at University of California at Berkeley. So here you can see the different transistor models. This is your FinFET on bulk. This is FinFET on SOI. This is vertical common gate FET, and twin silicon nanowire FET, horizontal nanowire FET. So these are different transistor models. So these different transistor models are used extensively in the future, will be used extensively in future integrated circuit designs. Okay, so variations in FinFET. So now we will discuss the different variations in FinFET. Like we have tall FinFETs, short FinFET, and the nanowire FinFET. So this nanowire, let's start from this nanowire FinFET. So this nanowire FinFET gives the gate even more better control over the silicon wire by surrounding it. And this short FinFET has the advantage of less challenging lithography and the etching. The tall FinFET, it has the advantage of providing a large width and therefore large on current while occupying a small footprint. So here you can see the different variations in the FinFET. It may be tall FinFET, short FinFET, and the nanowire FinFET. So as you know that we are designing new integrated circuits, and in our future integrated circuits we are looking for more and more number of transistors inside a small silicon area. Like in this year 2020 the chip we are fabricating, they will have around 15 or 16 billion transistors inside our small integrated circuits. So smaller is obviously better, so we have to fabricate more and more number of transistors inside small silicon area. So that's why we need the scaling of this transistors. So smaller is better. Why? Because the MOSFET performance improves as size scale down. How it improves? So in this figure you can see that this is your MOSFET, this FinFET structure, and here you see that as you scale down your device, switching speed increases. So here you can see switching speed increases and the energy consumption decreases. So energy consumption means your power dissipation per transistor, because this power dissipation is a major challenge in our integrated circuits, because our integrated circuits are getting complex day by day, because we are having more and more number of transistors inside the small silicon area. Okay, so scaling down is a good thing, and we need to continually scale down our transistors to fabricate the future integrated circuits. Okay, so what is going to happen in the future? So that's a big question. So still no one knows. So what is going to happen in the future? So still people are working on different techniques like maybe quantum computing or the molecular electronics or the different or the different uh, structure, or maybe the future we may work on the 3D IC technology. So there are a lot of options. We will have to think about that. So the end of silicon is near. So that's what the people and the research is predicting. Okay, so this was our lecture about the transistor structures and the future integrated circuits. So if you have any question, please don't hesitate to ask me. So in the first slide, you can see my email IDs, and you are welcome to contact by email, or you can also comment on the channel, and I will reply you as soon as possible. Okay, thank you very much for today. See you next time.